Good evening. I'm Spot On Weather meteorologist Matthew Euler. Welcome to the Spot On Weather 2022-23 winter forecast. This is part 5, 6 total parts in the winter forecast video series. This is part 5. This is additional factors that we're taking a look at for the winter forecast. And in general, if we look at this beautiful snowflake captured here this evening, just what it looks like here close up. There's a lot of great photographs of snowflakes these days out there. I've seen quite a few on social media shared. And this is one of the symbols of winter, of course, across the northern hemisphere. So let's get right into the factors, the additional factors. And I did some research today, just kind of looking over some of these and how they could potentially impact our upcoming winter season. And in general, this is what I'm going to cover in tonight's video. We'll talk about Arctic sea ice extent departures, the Siberian snow cover extent departures, solar activity, volcanic eruptions, sea surface temperature anomalies, as well as the East Coast winter storm history. All right, so let's first kick it off by talking about Arctic sea ice extent. What is the importance of having Arctic sea ice up in the higher latitudes, up in that polar area? White or light gray colored sea ice, whenever it's a white or light colored surface, such as this ice, this reflects up to 80% of the incoming solar radiation. So we have a high albedo with a white or lightly gray colored ice, and that reflects up to 80% of the incoming solar radiation. And what that does then is results in a cooler overlying air mass over an ice area. What happens with this Arctic amplification is you get more melting of the ice, and with that increase in the melting of the ice, instead of that incoming solar radiation being reflected and having the high albedo or reflectivity, it's instead absorbed. That radiation is absorbed by the open water surface, and that tends to warm the overlying air mass above the water in the Arctic area, resulting in additional sea ice loss. It's like a positive feedback loop where you get incoming solar radiation, there's less ice, it gets absorbed, the overlying air mass above the water is going to be warmer. So another big point I want to make about Arctic sea ice extent, and research is out there that correlates less sea ice extent in the Arctic leads to a weaker polar front jet stream, and overall, this makes a lot of sense. You have a weaker polar front jet stream because you have a weaker temperature gradient between the polar areas and the lower latitudes. So the air mass doesn't get as cold. The ice is missing up in the Arctic areas. So you have a weaker temperature gradient from north to south across the northern hemisphere. And that leads to that weaker jet stream overall. And that also leads to a more meridional or wavy polar front jet stream and colder mid-latitude temperatures. And that also, with that highly amplified meridional polar front jet stream or long wave pattern, it tends to lead to what's known as a negative North Atlantic Oscillation, or NAO. Here are some examples. I captured a couple images here. This was the blue solid line is what I want you to pay attention to. In addition, you'll see this dash line in both of these diagrams. Now, this dash line represents the record low sea ice in September of 2012 across the Arctic area. The blue line represents where things are at the time of these graphics. So this is September of 2021, showing you where this blue line ends up, somewhere between that 4 and 6 millions of square kilometers extent of the Arctic sea ice. This was last September. This is this September in 2022. And notice it's very similar to last September, maybe slightly lower, but not by much. Generally, we're looking at just below 5 millions of square kilometers of Arctic sea ice for this year as compared to last year. So not much difference, very similar in the extents. I did take a look at the one today for October 4th. The most recent one was October 4th of 2022. and it's still slightly below the normal where it would be. This is the median, by the way, this gray line, and you can see that the Arctic sea ice extent is fairly low, but not as low as the record back in 2012. Just in general, the lower the sea ice extent, again, that tends to lead to a greater probability for blocking patterns across the northern hemisphere. Below average in October, again, it's not as low as the record minimum we saw back in 2012. Now, let's take a look at Siberian snow cover extent and departures right now. Right now, this is the October 4th. This is the latest graphic I pulled from the Rutgers Global Snow Lab. Any of these brown colorings here indicate where there's actual snow cover on the ground across the high north, across parts of Siberia, northern Canada, over Greenland right now. You see where the snow cover is located. Why do we look at snow cover, by the way? What's so important about Siberian snow cover extent? Research has indicated that more snowpack over Siberia yields much colder air masses that develop over Siberia. Kind of like that positive feedback loop I talked about with the Arctic sea ice, where you get snowpack also has a very high albedo or reflectivity. So generally when you have more amounts of snowpack, a greater extent of snow cover, that generally tends to refrigerate the overlying air mass and results in stronger Siberian high pressure systems, much colder air masses as, say, compared to a ground that is not snow covered. High albedo or reflectivity incoming solar radiation hits that snow cover, and the energy goes right back out into space. It does not do much as far as warming effects. So we see stronger anticyclones over Siberian snowpack. And we get more of that Ural, Scandinavia ridging, that big, huge upper-level ridge in the troposphere to send that vertical energy propagating back into the stratosphere, ultimately weakening in the stratospheric polar vortex. I talked a lot about the SPV, or the polar vortex, last night. Please feel free to go back and look at that video again. But this is the importance of the Siberian snow cover extent in October. Here are some examples of where in past seasons that snow cover extent, how extensive it was in Eurasia. So you see, look how high some of these amounts were, but this of course is during the heart of winter season. But if we focus solely on October, we see that in the past years we have seen a steep climb in the snow cover extent across Siberia. The green here indicates last year, the 2021-22 October, and then the red line here is indicating the increase that's ongoing right now with that Siberian snow cover extent. And overall, research has indicated that above normal Siberian snow cover not only leads to those much colder air masses due to that positive feedback loop, but specifically in October, when they have an above normal level of Siberian snow cover, it yields a predominantly negative North Atlantic oscillation in winter across North America, and an overall weakened stratospheric polar vortex. So this is why this is an additional factor we need to take into account. What is it looking like today? We kind of see what the extent is. By the way, the Rutgers Global Snow Lab is just an awesome website. Just Google Rutgers Global Snow Lab. You can even look at the snowfall departures from climatological normals. So it'll be interesting to continue to watch this as we progress through the month of October to see how great this extent has been. I know the models have been bullish lately on really expanding the Siberian snow cover. It's off to a good start so far. One other factor I'd like to talk about is the solar activity. Now, this particular graphic goes all the way back to 1913. This is a magnetic flux in Maxwell's. The pink line on this graphic is a simulated predicted sunspot cycle flux, and then the black line is the actual observed sunspot cycle flux. So the sun has a naturally occurring cycle of increased and decreased activity. This typically occurs on an 11-year cycle. The sunspot numbers increase or decrease. Typically when we have a lot more sunspots on the surface of the sun, we tend to have much more active solar activity. This could eject plenty of electrons and charged particles in the upper atmosphere and really impact our life here on Earth, not only in the weather, but also in other means, such as our communication being lost, completely losing power grids, which has happened before with some really strong solar activity in eastern Canada back in 1989. But in general, where are we at right now in this graphic? We're in solar cycle 25 now, and we're starting to see an increase. After we had a lull in the solar activity the past couple winter seasons, we're now heading onto an increase, as noted by this pink line. This is the simulated, and then also the black line here showing observed. So we are on the way back up. We're having more activity. And why is this important to the weather for the winter season? Because research has indicated an increasing frequency of high latitude blocking, or that wavy or meridional jet stream, which you have these huge upper level ridges extending into far northern latitudes anomalously. These tend to occur, these high latitude upper level ridges and blocking situations, during lower solar activity, leading to a more stagnant weather pattern and a meridional jet stream. So now we're actually heading into increased solar activity, right? So it'll be interesting to see how this turns out, the solar activity in conjunction with the frequency of high latitude blocking. Now we're in a more active part of that solar cycle now here, solar cycle 25. And, if we increase the solar activity, then we would expect to see milder temps and less high latitude blocking, leading to a positive NAO phase, vice a negative NAO phase. And so this is going to be interesting to watch over time. But there's been research that indicates these particular patterns. Additionally, on tonight's video, I'd like to talk briefly about volcanic eruptions. This picture is Mount Pinatubo in the Philippines back in 1991. This was a real explosive blast of ash, sulfur dioxide, some of the dust into the far, far upper reaches of the atmosphere. This cloud extended all the way up into the stratosphere, that second layer of the atmosphere. And sulfur dioxide in particular is really good about reflecting incoming solar radiation back to space. And so there was actually a lower global temperature period, almost a whole degree Fahrenheit, for up to 1 year after Mount Pinatubo erupted in the Philippines. What are the most impactful volcanic eruptions for the weather are the ones that occur in the tropical latitudes. So volcanoes impact the atmosphere, there's no doubt about it. We've seen the cooling periods after these land-based volcanic eruptions. We see gases, dust, ash cool the planet by blocking the incoming solar radiation, and that cooling effect can then last up to months to years depending on the volcanic eruption characteristics. How powerful was it? How much ash and material dust and debris did it inject in the upper atmosphere? And due to these atmospheric circulation patterns across the globe, these volcanic eruptions in the tropics, again, tend to have the most impact globally on the weather. Eruptions in the middle to higher latitudes typically only impact the hemisphere in which they occurred. Here is the most recent volcanic eruption that we saw back in January of 2022, right around the mid part of the month, earlier this year. This was the Hunga eruption. This occurred in the South Pacific Ocean. What's interesting about this one is this was a submarine volcano. This was a volcano that was on the ocean floor that just blew its top, literally. And what it did is it ejected a lot of water vapor up into the higher reaches of the atmosphere, particularly the stratosphere. So we now have data showing increased levels of water vapor in the stratosphere from the Hunga eruption in January 2022, early this year. So volcanoes not only can produce a cooling effect to the Earth's weather, but they can also release these large amounts of greenhouse gases, such as that water vapor, as well as CO2, the carbon dioxide. This tends to lead to increased or warming temperatures, believe it or not. Being again that this was an underwater volcanic eruption in the South Pacific, this released tons of water vapor high into the stratosphere. In fact, this was one of the most powerful volcanoes since Krakatoa in 1883. The excess water vapor, what happens then, once it gets into the upper reaches in the stratosphere, which, by the way, the stratosphere, the second layer of the atmosphere, very important for us, specifically for the winter, because the stratospheric polar vortex, from my last video, I talked about that with sudden stratospheric warmings and how that can play into the strength of that stratospheric polar vortex. Usually the stratosphere is very dry, but now we got all this tons of water vapor into the stratosphere, and that can act as that greenhouse gas and actually trap heat beneath it. And that could also result in warmer temperatures of the Earth's surface. And this could last on the order of years. It's going to be interesting to see how this plays out into the strength of the polar vortex in the stratosphere this year, as well as just the behavior of the stratosphere in general. Now let's take a look at the sea surface temperature anomalies portion for additional considerations. This graphic here, courtesy of Tropical Tidbits, this is the September 2022. This was just last month, showing this darker blue shading across the equatorial, the eastern, and extending out to the central Pacific along the equator. This blue shading indicating the cooler than normal temps across the equatorial, eastern, and central Pacific. This is associated with the La Nina that's going on right now. Other features I like to look at on these sea surface temperature anomalies charts. By the way, blue is cooler than normal water temperatures, and the orange is above normal water temperatures, warmer than normal. So look what's going on here. High latitudes, Northwest Pacific, even off the U.S. West Coast here, the Eastern Pacific into the Gulf of Alaska, warmer than normal, much warmer than normal, associated with that positive AMO, the Atlantic multi-decadal oscillation south of Greenland. Look at these waters. Notice how water got cooler than normal temporarily, and that was mainly due to Fiona, which really went all the way up to Brunswick there, New Brunswick, and just Nova Scotia area, and just, you remember seeing this a couple weeks ago on the news. So the hurricane activities, these storm activities lately on the East Coast has resulted in a stirring up of the surface water, and when that wind mixes that surface layer up, you typically get upwelling, where you have cooler than normal water rising to the top from below. Right now, what we have in place, the key components of the sea surface temperature anomaly analysis for September 2022 is a positive Pacific decadal oscillation, or PDO. We have warmer than normal temperatures there in the Eastern Pacific, and then a positive Atlantic multi-decadal oscillation, or AMO, there south of Greenland. Look at the warmer waters, cooler waters, and then warmer waters. Talked about that in a previous video as well here in the winter weather forecast series. Again, here's my main key points. Extremely above normal in the northwestern Pacific, southeast of the Kamchatka Peninsula. And then, again, a lot of warmer than normal water across the northern latitudes. One thing I wanted to mention before I move on is just because it looks like this today doesn't necessarily mean it's going to stay that way for the whole upcoming winter. There could be a lot more activity with the storm track here. Again, those storms tend to stir up, the stronger winds tend to stir up the ocean surface. And then what happens is you get cooler water from below that comes to the surface, and it kind of cools off the entire water column. So just keep that in mind. Here was September of 2021 sea surface temperature anomalies. Notice the maroon and the orangish colors. Again, warmer than normal waters in the higher latitudes in the North Atlantic and the North Pacific. So this was last year, very similar. One difference I do note is a little bit of cooler than normal waters there, associated with more of a negative PDO along the Eastern Pacific off the U.S. West Coast. And then the La Nina definitely didn't look as strong, right? Last year in September as it did this year. See that? So we have a much stronger La Nina. It's established, it's firmly in control this particular September as compared to last September. Now what I did on the next set of slides is I went back and looked at sea surface temperature anomalies, and then I compared them to the air temperature anomalies for the winters. And each of these graphics is going to show you on the next slide, upcoming slides, I'm going to show you sea surface temperature anomalies. Blue is below normal water temps, and orange is above normal water temps. Well, I'm going to show you what it looked like in specific warm past eastern winters and cold past eastern winters. And in general, I took a snippet or a snapshot of Decembers of select years going back to the year 2000, just to kind of see if there's any kind of correlation between how the sea surface temperature anomalies looked and what kind of temperatures we got, whether they were above or below. So you see here, the first shot I'm taking is we're looking at past warm eastern winter sea surface temperature anomalies. I'm going to take a look at that over the next 3 slides, starting with this one. In this particular image, we see this is December of 2007. We had a below normal water temperature setup, La Nina across the eastern and central equatorial Pacific. We saw some negative PDO here with cooler than normal water over the eastern Pacific. We also had some cooler than normal water there off the U.S. East Coast in December of 2007. And this is how the overall winter went from December 2007 to February 2008. The yellow coloring, by the way, indicates above normal temperatures for the winter. The green coloring or the blue coloring indicates below normal temperatures. So with a La Nina and a negative PDO, we saw above normal temperatures across the Carolinas, specifically in the southeastern Virginia, all the way up into parts of New England. Florida was also above normal by 1 to 1.5 degrees Fahrenheit. Let's take a look at December 2011, another past warm eastern winter. These were the sea surface temperature anomalies for December of 2011. Notice we had a La Nina and a negative PDO, Pacific Decadal Oscillation, with cool temperatures, cooler than normal temps off the eastern Pacific into the Gulf of Alaska. And notice this warmer than normal area again back towards the northwest Pacific, a little bit stronger than the December 2007 case. And in general, this is how that particular winter ended up. From December 2011 to February 2012, this orange coloring indicating temperatures on the order of 2 degrees Fahrenheit above normal for a large chunk of the upper plains, upper Midwest, Ohio Valley, New England, all the way down to the Gulf Coast. So pretty mild winter 2011-2012 for the eastern U.S. And then the last sample I'll show you of a past warm eastern winter occurred back in the 2015-2016 winter season. And this affected quite a few people, not even just the East Coast, but this expanded west, all the way to the West Coast this particular winter. We had a very strong El Nino. Look how dark these colors are, indicating much above normal sea surface temperatures across the equatorial eastern and central Pacific. We also had a positive PDO, above normal sea surface temperatures there, from the Gulf of Alaska right on down the East Pacific along the U.S. West Coast. And then look at this. Even the East Coast had much above normal water temperatures. The Gulf of Mexico did, right off of Baja. I mean, the oceans were really, really warm this particular winter. We had a combination of these two factors when you get an El Nino and that positive PDO. They tend to, it's constructive feedback basically, where they both align with each other and produce more enhanced warming effects across the U.S. Look at these temperatures and how far above normal they were in the winter of 2015-16. Look at New England in particular, 2 to 3 degrees Fahrenheit above normal mean temperature. Wow. And there wasn't many cool spots. There's no green or blue coloring at all for that particular winter here in the U.S. Now let's flip the switch and go to the past cold eastern winters. I'm doing 3 sample sets, 3 specific years once more. And then I'll show you the complete data set, what my results were anyway. All right, so first we'll start off with December of 2000. Now, what's so important about the winter of 2000-2001? And I mentioned this in the La Nina portion, the La Nina video here, the winter forecast series. This was a third consecutive winter with La Nina conditions across the eastern and central equatorial Pacific. See the blue shading? So we had La Nina and we had a negative PDO, below normal sea surface temperatures along the U.S. West Coast and into the eastern Pacific. And then look at this chunk. This is pretty cold, below normal. They are north of a above normal water temperature situation. This kind of setup would promote more of a west to east jet stream across the Pacific. But in general, what we had is a La Nina and a negative PDO in December of 2000. That's this particular sea surface temperature anomaly chart. And then this was the winter, the air temperatures. A large chunk of the country from the Rockies east, all the way to the East Coast and down to the Gulf Coast, with the coldest below normal anomalies across parts of Kansas, Minnesota, and Iowa in the winter of 2000-2001. But it was a colder than normal winter overall. Now this is, again, we're entering a third winter, consecutive winter with La Nina this year, a triple dip La Nina. So we'll see. I like to correlate this and see what happens. Looking at the December 2010, this winter here, the 2010-2011 winter, was also a colder than normal winter east of the Rocky Mountains. You see the green coloring all the way down to Florida. The only place really in the east that had above normal temperatures, and they were only by about 0.5, half a degree Fahrenheit, was up in Maine in the winter of 2010-2011. Look how strong the La Nina was this year. This was December 2010, sea surface temperature anomalies. And look how much below normal the water temperatures were across the Gulf of Alaska, down the eastern Pacific off the west coast. And also, look how below normal the water temperatures were in the Gulf of Mexico, along the U.S. East Coast in December of 2010. This was a pretty cold winter, and look at the temperatures here, the air temperatures. And by the way, it also was a strong La Nina year. The December 2014 sea surface temperature anomalies, things switched and turned around again. We had above normal water temperatures in the equatorial, eastern, and central Pacific associated with El Nino. We also had a positive PDO, very much above normal water temperatures in December 2014 off the U.S. West Coast into the Gulf of Alaska. We also had above normal water temperatures across the North Atlantic. And look at the air temperatures this particular year. This was a nation divided, a split right down the middle here in the central U.S. Much below normal east of the central U.S. and much above normal over the western U.S. I was out in San Diego at the time, and it was just crazy. They normally get their rain in the wintertime. And even with the El Nino, there wasn't much rain occurring. It was very dry winter that winter out in San Diego. It was very much above normal all winter long, while the east was shivering, especially as we got towards February of 2015. So overall, these were my sample sets. I just wanted to compare sea surface temperature anomalies with some of the more memorable, warmer or colder than normal winters for the eastern U.S. And I'm also showing the other parts of the country as well. If you live, let's say, out in the western U.S., you can kind of compare these patterns. In my case of research here, I really couldn't connect a specific correlation with the El Nino La Nina and the negative PDO, positive PDO. I was looking specifically out in the Pacific when I was putting these slides together, and that's really what I display here. So I really didn't have any direct correlations, but I'm going to keep researching this. And then overall, this was my summation. I looked at, I went back to the year 2000 in this research, and I discovered there were 8 El Nino winters with above normal water in the eastern and central equatorial Pacific. And there were 8 La Nina winters, below normal water temperatures across the eastern and central equatorial Pacific. And this is what I discovered. With the 8 El Nino winters, they resulted in 4 warmer than normal and 4 colder than normal winters across the eastern U.S. So it was a split down the middle of the 8 El Nino winters. And then the 8 La Nina winters resulted in a bias towards warmer than normal temps in the east. 6 warmer than normal winters and 2 colder than normal winters across the eastern U.S. And you'd expect that with La Nina, right? The typical pattern with La Nina is a milder and drier winter for a large part of the eastern U.S. Definitely the southeast, definitely the southern U.S. So real interesting. This is what after my research, what the total summation of everything. Now, I wanted to mention a couple other things about these anomalous pockets of either warm or below normal water temperatures. This was called the warm blob. This was extremely above normal ring of water across the northeastern Pacific Ocean. This is February of 2014 in the upper right. This is April of 2015, and this is September of 2016. In all 3 cases, you'll see temperatures in the order of 2.5 degrees, and I believe, this is Celsius, 2.5 degrees Celsius above normal, 2.5 to 3 degrees Celsius above normal water in the darker maroon rings here. Of course, this one here really played into some of the atmospheric feedback processes. We had a general upper-level ridge parked over the northeastern Pacific. This was known as the ridiculous resilient ridge, triple R. And it's set up the long-wave pattern is set up to be just this highly amplified ridge in this eastern Pacific area, and then a massive downstream trough from the Midwest to the East Coast, resulting in very, very cold temperatures. And you kind of see the progression of this as we get to September 2016 here. And there is the summation of it. We saw a massive upper-level ridge across the western U.S., very abnormally dry and very mild, and deep downstream trough over the eastern U.S., very stormy with very cold temperatures. This is just one example of how sea surface temperature anomalies can really make an impact, especially when we talk about the Pacific, because as you know, the wind blows from west to east in the middle latitude belt, so what happens upstream definitely does matter on the downstream weather. And this was the November 2013 to February 2014 time period on the left. This was on the right is the November 2014 to February 2015 time period on the right. In both cases, this overall pattern featured a positive PNA and a negative, we saw colder than normal or troughing there southeast of Greenland. But in general, it was very, very cold in this particular area. The upper plains, Midwest, really took the brunt of the cold. And we saw much above normal temperatures over the western U.S. And then in November 2014, February 2015, a similar pattern. Positive PNA, ridge over the west, trough over the east. Okay, and then in this case, a little bit different in the November 2014 to February 2015 period because we have more of an upper level ridge kind of poking its way up into the building into the North Atlantic as compared to the previous year. Finally, I'm going to end this part 5 of the winter forecast video series with East Coast winter storm history. It's abbreviated ECWS, East Coast winter storms. And this data, by the way, is courtesy of Cornell University. These are the defining factors when we look at the history of both East Coast winter storms and strong East Coast winter storms. Now, East Coast winter storm is simply a cyclone with winds less than 52 miles per hour, while a strong East Coast winter storm is one in which winds exceed 52 miles per hour. I did my master's degree. I did some research on this. I was correlating the accumulated cyclone energy from the hurricane season in the Atlantic, the North Atlantic, and I never really did come up with the correlation between accumulated cyclone energy, potential energy during weaker hurricane or lower or quieter hurricane seasons as compared to the preceding winter season. But in general, if you look at some of the graphics here, this goes back to 1990, again, data courtesy of Cornell University, you'll see the numbers vary from year to year. Some years have a lot. Some more active recent years, for example, that I'm highlighting on the slide was in 2019 when we saw 30 East Coast winter storms and 20 strong East Coast winter storms. That was a fairly active season. 2018 as well. We had that monster bomb off the East Coast in early January of 2018. I'll never forget that one. East Coast winter storms were 29 that particular year, 16 strong. And then 2017 was another active year, 26 East Coast winter storms, 13 strong. And all the way down to 2009 and 2007. Now, the least active recent years include 2015, 2012, and 2011. And you can kind of see the numbers here. There were only 19 East Coast winter storms in 2015. That was the winter, we looked at that one. That was a strong El Nino winter. So that was a very mild winter. It seemed like there was a ridge off the southeast coast a lot that winter. Additionally, 2012 was pretty limited in the number of East Coast winter storms and strong East Coast winter storms. And then 2011, look at this, only 5 strong East Coast winter storms in the year 2011. These are the defining definitions of East Coast winter storms. These are also known as nor'easters for those that live along the East Coast. And these storms typically move from the southwest to the northeast along the U.S. East Coast, or maybe just slightly offshore. This is from the paper by Hirsch et al. In 2000. These are the criteria for East Coast winter storms. Must have a closed circulation, so you have a closed isobar around the low pressure, be located within this quadrilateral bounded box, 45 north by 65 west and 70 west, and at 30 north by 85 west and 75 west. And the general characteristics of East Coast winter storms show general movement from the south-southwest to the north-northeast, and they contain winds greater generally than 23 miles per hour sustained. And the conditions must persist for at least a 12-hour period. So these were the criteria put out by Hirsch et al. In 2000 in a paper that was written. And Cornell University still tracks the numbers here, which I find real interesting. Again, to see if there's any patterns in these numbers in the amount of nor'easters or East Coast winter storms we see from one winter to the next. All right. I think I'm done with this video now. Just wanted to cover some additional winter season forecast factors. Okay, so we covered quite a bit tonight. We covered Arctic Sea extent departures, talked about the importance of why that matters. We covered Siberian snow cover extent departures, specifically in the month of October. We talked about solar activity, whether there's high or lower levels of solar activity. Has to do with the 11-year solar cycle. Volcanic eruptions and the impact they can play, both a cooling and a warming effect, as well as sea surface temperature anomalies. And we looked at correlating those anomalies with previous warm and colder than normal winters across the eastern U.S. And then finally, we took a quick look at the East Coast winter storm climatology or data set, the history. We're looking at, I'm continuing to look into research on particularly this area, the last bullet, East Coast winter storm history, to see if there's any correlation in the numbers from year to year, or if there's any kind of pattern there, right? Additionally, I'll be continuing to do some research, and I'll be curious to see how the volcano, the Hunga Tonga eruption earlier in January 2022, how this impacts the global weather overall, specifically our northern hemisphere winter this year. Is this going to result, that increase in water vapor, of a warmer polar vortex, or warmer surface temperatures is what I meant. We'll have to see what happens. Okay. And so there's a lot to talk about here. There's a lot of additional factors that go into the winter weather forecast. And I, again, spend extensive amounts of time digging into the research papers and seeing what I can pull out from those, the main points from these research papers, in talking to you in these videos about these various aspects that impact our winter weather in the United States, as well as further to the east and the northern hemisphere over parts of Europe, as well as Siberia, Eurasia. All right, that wraps things up tonight. You know what? The next video will be my final video for the winter weather forecast for 2022-23, and I'm going to show you my overall weighted factors for my winter outlook, as well as my maps showing in the United States where I expect warmer or colder than normal temperatures, as well as below or above normal precipitation. So I cannot wait. I'm going to work on finishing that up. And thank you again for subscribing to the Spot on Weather YouTube channel. Certainly hope you learned great things. Appreciate the feedback I'm getting in these videos. I really appreciate the comments, and I really appreciate you enjoying the channel. Right, that wraps things up tonight, and until next time, I want to say take care and God bless everyone.